Welcome to Circuit Valley. I'm Gaurav. Today I'm going to talk about this behemoth of an instrument which you see in front of you. It's a really niche instrument, TDS8000 digital sampling oscilloscope. It's not your normal oscilloscope. They are also called CSA 8000, and this just happened to be TDS8000 model of it. And these specific oscilloscope, they are meant for really special purpose. They are meant for specifically signal analysis. For example, eyes diagram, jitters, rise times, and TDR analysis. And they are also meant for primarily communication systems, and you can also measure with them your impedances of traces of cables and everything else. You can definitely do really good TDR. This oscilloscope accepts multiple type of different modules. These big slots which you see in front of you, these are for optical modules, and small slots are for communication modules. Small slots are for electrical modules. So this oscilloscope by default does not have any inputs to sample or display the waveform of. You need to have a module or a sampling head, it's called, connected there, and then it will show you anything. Oscilloscope which you may be having at your home maybe goes to a gigahertz or something like that, but this particular instrument, depending on the sampling head, can reach to 70 gigahertz. Yes, I did not say that wrong. It is really 70 gigahertz. I have two electrical sampling heads for it, and one model is called ATE01 and another is called ATE04. ATE01 is a 50 gigahertz sampling head, and ATE04 is a 20 gigahertz sampling head, and it also has a TDR function. Maybe you can observe that it is having a problem. It does not boot into the application. There is certainly something wrong with this instrument. I have bought it as a defective instrument, so we'll try to find out what does it do and how do we possibly repair it. Okay, so you can see, I'll show you this app. So I'll show you this app. This is my mouse, and regardless how long I wait, this TDS application will not start. I'll show you around the oscilloscope. What is it running? It's running Windows XP. In my case, they run Windows 98, Windows 2000 as well. Okay, maybe I'll shut it down. I have turned it off, and I'll show you around. So these are the slots which I was talking about. The bottom, small CH1, CH2, CH3, CH4. These small slots, they are for electrical sampling heads, and bigger slots for optical sampling head. It can do analysis over fiber and these kind of communication systems as well. Instrument looks really basic. This is the model TDS8000 digital sampling oscilloscope. There's a floppy in front and a control system. There are trigger inputs as well. There are two trigger inputs. One is 2 to 10 gigahertz. Another is DC to 3 gigahertz. So one is pre-scaled input. These are SMA connectors. If you want, you can remove them. There is no information available. There is not even a single video available about TDS8000. So this is going to be a very first video published on YouTube about repair of TDS8000, and we will see how it goes. I'll show you on the back. In the back of the instrument, you see a normal Intel PC motherboard cut out there. This is a normal Intel PC motherboard, a Windows XP license, and the serial number and everything else. And this is the power input. And there's a USB as well. There's just one single USB. This is the DVD drive, and there's the hard drive. Hard drive can be pulled out. There's a serial port, display output, printer port. I have not seen this thing in a long time. And there is a card bus as well. There's not much going on in the back. There are two fuses, and that's it. So I'll try to take it apart and we'll see how the repair goes. So I'll first take out the screws on the top, and then we'll go from there. I'll use my trusty Vera. Let's see what kind of bit it will take. Yeah, perfect fit. So it takes TX15, ROX 15, screws are out. These are the screws which they may be using to hold the accessory bag as well. Yeah, and this thing should be able to lift up, I hope. This is the first time I'm doing it, so you are seeing along with me. Yeah, so these were the clips, two clips, they were holding it, and that was the reason, this clip and that clip on the side, there was nothing else there. Take this thing apart, top cover, I'll take out the handle. There are many screws on the top. They are all same sizes. Maybe I'll mark them because I have to put them back. So this top plate should be out now, I hope, if it is not being held by something. Yeah, so this slides, side slides like this, and you take out the side, it slides like this way. Maybe I'll show you. So it was hooked like that, and it just slides out and gets out. So it's very easy to take out. Same thing is here as well. Side slides. They're already marked, but I'll still mark them from my own satisfaction. It appears to be that the whole thing comes out and everything else, because it appears to be that no, it doesn't come out like that. You may need to take the whole bottom out. So this also comes out very easily. They are different actually, they are different because it has a hand. So you have to take out these bottom things. I hope it doesn't have a screw in this rubber feet thing. We'll find out. I'll take out the only one which are holding the sheet together. There are two different types. Few sits in, this sits in, this was out, and you see down there, there's few sit in and few of them are out actually. This is out, this is sits in, so I'll just take the out ones and see if it comes out easily. The screw appears to be, all of the screws are same, but I'm still keeping them separate so that I can know that I'm not putting something wrong. Yeah, so this comes out. So you see this comes out very easily. Put it aside. And we have access to the scope. It appears to be that whole sheets comes out together. So I'll take it apart. It's out, hanging there. We'll take out these three screws as well. They are all the same size, we'll still keep them away. One of the side panel is out. I believe we don't need to take both of the side panels out, because thing which you see in front of you, this primary board is a normal Intel motherboard, Intel CPU Celeron is under there. This is the 256, total 512 megabytes of RAM. The board on the bottom which you see, This is the primary board which runs VxWorks operating system. This runs Windows, and these two boards need to communicate, and they communicate using this little PCB. I have read on internet quite a bit about this series of oscilloscopes, so I know how they are built. Some of them also get corrupted CPLD, but most of the time it's corrupted RTC, which causes it to forget its boot setting, and this secondary board doesn't boot. Primary board boots, but secondary board doesn't boot. And this is a display, a little display of a single segment display. It shows you the board status of the VxWorks board, and we will try to power it on the board, and we will see how does it behave. There's also one battery. I don't know if it is dead or not. We will try to measure it soon. This is definitely could be dead. The instrument was last opened like 20 years ago or something like that. I'll get my multimeter, put this thing there. We'll try to measure it in circuit. Okay, so I hope the ground is ground. Ground is chassis ground, and I'll just take it from here, and maybe you will want to see with me. So we have lights on. We are measuring 2.8 volts. It's not completely dead. It's still somewhat operational, and it will do for next 20-30 minutes when I'm going to power this instrument. When we power this, we will monitor this 7-segment display, because I have read online that when this board is broken, the 7-segment display, it shows you the status, but board without appropriate setting keeps booting one after another, and that's why it does not have appropriate boot settings and keep resetting. And so then you will have some kind of repetitive display on the board. Let's see. So you can see the displays right here. Maybe you cannot see, I'll tilt a bit. This is the display. I'll turn the board on. You see 5B. So the display is upside down. The 7, this means a issue. 7 means a issue. 5, 9. It's not. I don't know. It's 8 now. H, again 7, and it will keep doing this thing again and again and again and again. And you will see the board primary application. The primary problem with this instrument, why it's not starting, is that application starts, application waits for this board, this acquisition board to start, this VxWorks board, but it cannot find the appropriate setting which is supposed to come from memory on this board. So that's why it's keep going round and round in the loop. So that's why you see it's not reaching a status. It goes into this 8 and now H, 7. It will keep repeating. There is a memory, I'll show you in a second. I have to take out this board to reach to that memory, and we will try to fix that memory as well. Maybe we'll need to replace the memory, or we just need to replace the power itself. This CMOS battery I have replaced, and to be able to access the VxWorks configuration memory which is on the VxWorks board, I need to take out this whole motherboard. For that I need to take out few screws. It's a similar process. Let's do it as well. We'll take out everything one by one. Two screws goes for the floppy drive. It comes out. There's one screw on the top here. There are further screws. So we're supposed to take out the screws which are holding the motherboard itself. Now let's see if it moves. I can see I lift it up. Take out the floppy drive, put it back on it. So this connector, this goes to the VxWorks board, and that's where all the magic happens of the oscilloscope. And we will put our this connector which you see, maybe I'll show you properly. This connector which you see, this goes to the VxWorks board, and that's where all the magic happens. And this is the configuration memory which was covered by this motherboard, and there's a battery on top of the NVRAM memory. And we're supposed to check that battery as well. We'll check the power consumption of the we will also check the power consumption of that particular NVRAM chip. I hope that is not consuming too much power. Otherwise we need to replace and find an alternative for that. There are multiple alternatives available. You can buy the whole NVRAM module from Maxim or Mauser, or you can also get FRAM modules available nowadays for this. So let's put this motherboard aside and we will focus just on the VxWorks board. So just to show you the close-up, this is the VxWorks board, and this connector is the terminal for the VxWorks. That's how you configure. This was the status display, and this is for FPGA configuration. This is how this connector, this is how it communicates to the Intel motherboard, and there's a side panel connector which communicates to the rest of the board. And so we will clean it a bit. You can see this all messed up, and as I said before, this is the RLS chip which has memory and battery. This little thing is the battery on the top of the chip or the module, and that's where all the configurations are saved. We will try to first change the battery, and then we will try if there is then we will try to figure out if the chip is faulty. If the chip is faulty, then we need to change the whole chip. So let's try to take the battery out. was quite violent, but I got it out. Somehow I got it out. This is how the battery looks. It sits on top of this module and supplies it power. And we'll measure this battery right now, and we'll see if it has any voltage on it still. I'll put it here. Maybe I'll not put it on the PCB itself, not to damage anything. So I'll show you. This battery is completely dead, absolutely dead. We'll replace this battery. We'll try to install the module one more time, this power PCAP module, and we'll see how it goes from there. I'll also show you the module. So this is the NVRAM module from the Dallas, and 4 contacts paired, which you see on the top. This is how this little power cap module supplies the power to it, and this is where all the VxWorks configurations are stored. We will try to load stuff from depending on what this memory says. When this battery goes down, this memory module cannot contain any data, so it also needs to somehow forgets everything, and that's how you got this guy not to boot. As you can see, this module has 4 contacts. Normally if you find photos on internet, you will have contacts with, or power cap module with 2 contacts. It has 4 contacts because it also have a crystal oscillator. You see in the corner this tiny little thing, and it appears to be a special module. We will find out. We will replace this battery first and then try to measure power consumption of the NVM module. If it consumes too much power, the module need to be replaced. See, I did not have the appropriate cell, so I just didn't replace it. I made this little thing. I'll glue this here with CR2032 on top. This will give you the possibility of measuring the current. I intentionally left 2 pins open. We will use hooks like this to connect, and I have really this kind of probes or leads. They will hook into this like this, and then I'll be able to connect my multimeter to it. So again, to test this power consumption of NVRAM module, I have hooked my multimeter in series and powered this NVRAM's backup cell from a bench power supply, and right now you can see the instrument is on and it's consuming around 0.02 microamp. I believe it's the residual. As I have told you, this RAMs have a lot of capacity. These RAMs need power, and now I will turn off the instrument and you will see if the power consumption change when instrument turns off. So Windows is shutting down and power consumption on. Now power consumption has gone to 550 nanoamperes. This should be good, but the problem is this chip is faulty in such a way that it's not even holding content even with low power consumption. So this chip need to be replaced. I have ordered already this replacement from Mauser, and let's see. The replacement chip I have ordered, it came from DigiKey, and you see this part number is a little bit different, DS1764, and it is 1646. Sorry, DS1746, and that's another one is DS1646. I have checked, they are pin compatible and all have same address pins and data pins and everything. This chip is a little bit larger. You can also install available FRAM modules as well, but I do not find any FRAM modules. There are some people who are selling them, but I do not find them anywhere in stock or available where I can purchase them quickly. So I quickly got it from DigiKey. I think I'll be set for maybe next 10 years. If it broke again, then I will replace them with the FRAM chip. So if you want to see in the back, this is how it looks on the back. There's a controller and a RAM IC, and there are these pins. This is not completely sitting on the PCB itself. These pins are keeping it a little bit higher, so we will use those pins as a lever here to be able to easily solder. We'll put solder this side, that side, and lift it on one side, and then lift it from the second side. It should be easy enough to do. I believe I can show you on video. We will try, because the problem is this is how it sits on my bench. My Mantis doesn't fit, and this old crusty Lupe or this lens is the only source of magnification there. I would like to change it in the instrument rather than taking the whole board out. I can do that as well, but I will not do it because I'm a little bit scared about this old crusty board. So you have to bear with me with the reflection. I cannot really put a camera somewhere from where the reflections cannot come. I do not have that much of a light setup, but under the microscope then I have to work, and we'll see how it goes. Maybe I'll edit this video a little bit so that it's not that boring, but this is how the chip looks. I'll put solder on the one side, and then we will try to desolder it. I use my thickest tip so that I can cover as many pads as possible. If you have a chisel tip with a long chisel, that can also work. This thick tip, it allows you to decent heat transfer as well, and you can touch up many pads. I'll keep the soldering temperature to as low as possible. I've set it to 270 degrees. Generally it's quite low for my work. I've put up quite a bit of solder there, so that all the pads have enough thermal mass to keep wet for a long time, and so that I can lift it from one side. We can clean it later. Now I'll use my plastic tweezer and try to lift it up from one side. Seems to help all that much. It's quite a bit lifted. I can see a few pads are gone, and you will see this IC has bulged, or this module has bulged. Now we'll try the other side, do the same thing. Okay, on that side is lifted quite a bit. So this side is completely clear. Now we should be able to easily. So one side is completely clear, and we should be able to easily take it out. The module is out, and you can see it. Maybe I'll focus here a bit, so you can see. Maybe I'll check the date code on it. How old is it? .0008. So, and both of the IC, one is 0023 and another is 0008. So both of them are exactly around 25 years old now. And the front module of the module also says 0036. So very, very old IC. Let's compare it with the new IC. So it says 2426. So it's somewhat new. Like it'll hold maybe another 25 years I hope. So let's clean, remove all the excess solder, and then we will do one more time soldering job. Let's clean it a bit. Maybe I'll keep using this big soldering tip and use the solder pump to get this big blob off. Otherwise I'll use a ton of desoldering wick, and they are quite expensive. Now most of it is gone. A little bit remaining, and now I'll use my wick. With a very tiny amount of flux. I don't want to flow the flux everywhere. Here too much flux can cause damage, I believe, because I don't want it to. I will not be able to completely clean it in ultrasonic cleaner or anything else. So you need to have a little bit flux, not much. Temperature is still very low. To keep the board from overheating, it's around 260 degrees in my JVC. So pads are clean, they are not flat. I will remove all the solder from them one by one. Clean up. I use some paper towel and some alcohol to get the rest of it out. I'll not soak it in alcohol, because if I soak it in alcohol, then alcohol will go everywhere. I don't want to do that. Now steady, I'll take another one. Place is pretty much clean. There is some solder left. I will do the same work one more time, because I do not have microscope. I cannot check, and that's why I have to redo it one more time. I will use my wick and try to clean everything. Maybe increase the temperature by 5 degrees. So there is some here. Quite a bit here. Now it's cleaner. It's very clean, very well done. So let's solder the new chip. Orientation is same exactly as before. Maybe I need to inspect it a bit because I don't see the pads properly, how they are aligned, how they are good or bad, or what is wrong with them. So soldering is somewhat hard because of the overhangs. There's a PCB hanging over to the PCBs hanging over to the pins, and you cannot clearly see the pins if you have soldered them or not. I'll try one more time. So what I do is I try them one by one and try to solder them. Which side is wet? It's not easy. So I'll do it off camera. I'll need a lens and you will not be able to see it then, because if I put a lens there, there's not much visible. This is the log which I stored from the terminal on the side, and you can see this little guy from the VxWorks. It outputs quite a bit of data, and I'll show you where the problem is. Problem is here. That boot device, it forgets, and I have configured the boot device appropriately. Here you have to press the button, C button, to start configuration, and then press dot to clear field, minus to go to previous field. So I have configured it properly. This is how I configured it, and after it will boot properly and happily. This is how it boots. This is the boot log, successful boot. And now after the battery change, it will also remember the settings. Everything will be fine. We will do many preventive maintenance on this board. We will reprogram the acquisition board FPGAs as well, because due to heat and everything else, they sometimes forgot their settings, or sometimes lose the configuration, and sometimes you have just one bit flip, which may cause you acquisition errors. That's another matter. We'll do some cleaning and everything else, and then we will be done with this scope. The VxWorks board, it shows D. If you read it from this side, shows D. So it's booted and it's ready for the commands to be accepted from the application. So it appears to be that due to these compensation errors and normal channel acquisition errors on the strobe, I think I want to verify if the content of the PLDs are correct. Some guy from Austria on AEB platform suggested that these PLDs, due to the heat and long operation, they can get bit flip or they get memory corruption and they need update. He has also published the web form files or bitstream files for them. I'll first read all the PLDs through this JTAG. You can see on your screen detail about the connector itself. And the files are available on my website and also available on AEB blog forum, of course. So we'll try to read these PLDs and try to reprogram them. So after initializing the chain, I have connected my JTAG to my TDS8000, and you see there are 10 PLDs, and 9 of them are same 95144 and 2 of them are 95216. So these 2 PLD, they will get a special config. The first one is also not a channel PLD, it's some kind of discrete or miscellaneous logic. This will get a special firmware, and these 4 will get a special firmware. I'm having this impact running on Windows 10, and it is having very much difficulties reading back the firmwares. So if I try to do read back, if I try to do read back on any of the PLDs, this whole application will crash and exit. So for some reason I cannot use impact GUI for reading, but there is another quirk. I can use the command line to read and write all of the FPGA. I can read all of them and write all of them except for the first one. This first one in the chain. This has nothing to do with the TDS8000. It has only to do with the impact running under Windows or modern Windows 10. I do not have the Windows 10 version of the ISE installed. I have this older version. Till now somehow it worked, but I don't know why it's failing now. So I'll just read all of them in the background and save them somewhere. So one thing you must notice that I'm reading MCS here, even though you must read JDEC. MCS is for memory configuration and JDEC is for PLD configuration. So if you want to read for usage to program it to another PLD, you should read JTEC file, JET file. Sorry, JET file. And I'm reading MCS. What is MCS brings me? It brings me that I can use MD5 sum or these kind of programs to compare, because when I read JED has a timestamp, so every file is automatically different. I need to manually compare them. So for the sake of easy comparison, I'm reading MCS file, all of them. I'll also of course read all the JET files. I also have a backup JET file which is available on my website. You can visit my website or on GitHub. And so I will read all of them. All of them have been read, and what I can do is I can do something like this: star.mcs. So these are the files which are read, and you can see it has been numbered. So I told you one is going to be unique, 2, 3, 4, 5. These 4 PLDs must be same. You can see the last one is not same, it's corrupted. Okay, and 5 and 6 are same, and they're also having the correct MD5 sum. And 8, 9, 2, 3 are exactly same. So there is a pattern there. And then number 10 is also good. And number 11 is definitely corrupted. And number 5 is also definitely corrupted. And I have the original files as well from my other instrument and also from internet. I can also compare the JET file. You don't necessarily need this weird trick with MCS file. But JET files also, the problem with JET files is that, as I told you, they have timestamp. So now that we programmed the FPGAs, so we'll try to see if we can use the instrument. To be able to perform some preventive maintenance on the unit, I'll take out the power supply board. It's supposed to take only 2 screws out and 3 screws in the back, and this power supply board will just lift out. Somewhat dirty, but it's not that bad. You can clean it. You can also inspect the capacitors if capacitors are damaged. They are not that new, so dates are marked 2001, quite old. So the board is sitting on the ESD mat and also connected to the mains but not turned on. And I'll have lightly brushed it. I'll also brush it a little bit more. Remove everything which is not appropriate. Maybe we can inspect it a little bit if something is burned out or capacitors are, any of them are bulging. Generally you can replace them, but they are just way too many at the moment for me to take on. So I'll not replace all of them. Maybe at some point I'll come back and replace them because they are pretty old. 2001 marked 24 years old now. They are like 24 years old now. Another part of the repair, sometimes this computer doesn't boot properly, and that it starts and hangs in the middle. So I have reseated these RAMs. They are 256 GB each. So I take them out, put a little bit alcohol and contact cleaner, not the corrosive part, and reseated the RAM 2-3 times, and that fixed that problem. About the hard drive, maybe I can show you. I have installed MSATA. I have installed MSATA to PATA adapter, and this maybe you can see in the corner. I don't want to maybe you can see in the corner, but it's from a company called German company called Reinforce, and it works really well. You can also upgrade them using CF card or something like that. And I'm also going to replace the thermal paste on this little guy and see if the thermal paste is dry or something like that. Dry it's not, but still we will put a little bit thermal paste there. It will provide us a little bit better thermal performance. You can see the little old Intel Celeron processor, pretty old thing. So now it's the time to put it back together, and you see these star-like marks. Wherever the star-like mark goes, you have to put a screw, and if there is no star there, you don't need to put a screw there. There may be some other screw coming in. For example, you see in there is no star mark because the side panel screw will be coming there, or what is the name, or the rack mount screws will be coming there, and so it's very easy to not miss any screws. And for example, these places there will be a top panel and its screws will come there. So keep watch, wherever the star is, there's a screw. So the repair is done and scope is booting successfully. I somehow managed to acquire some modules as well. I have 150 GHz module and this ATE04 20 GHz TDR module. It generates really fast 17.5 picosecond pulses, and you can see with the SSD drive is up, the system is booting real fast. The only primary delay is in the board itself. Windows doesn't take much time, but application itself takes quite a bit of time to boot. So Windows is up and running, and for some reason network was disabled in the back, and that's also I have fixed. I have enabled in the BIOS. Sorry, it was disabled in the BIOS. I have enabled it, and I hope to install some VNC software on this so that I can control it from my normal computer rather than fiddling with this front panel and everything and everything else, and get automated measurements, and so that I can print this stuff and make calibration reports and everything else. So it's booting. You have to have a little bit more patience. Maybe I'll speed up the footage a bit. No errors, everything is fine. Test is done. Signal trace is also on the screen. Signal test is done. No errors. Test is done. Signal trace is also on the screen. We have a functioning Tektronix TDS8000 oscilloscope, and we will do some real time. We will do some measurements with it. I'll show you how fast it can go. And that's it for this video. For more repair video, you can subscribe to my channel, and more electronics, FPGA and software related products. You can definitely subscribe. Keep watching. Thank you. Bye bye.